Picture this. You're sitting in your Cambridge IGCSE Physics exam. You found the exact right formula, plugged in the numbers, and confidently copied the final results straight from your calculator onto the page. You're feeling absolutely great about it, but let's immediately expose the one tiny exam mistake that costs students massive marks before they even realize what hit them. In this explainer, you just lost the mark, and you literally have no idea why.
Writing down exactly what your calculator spits out? Yeah, it feels right. I mean, calculators are perfectly accurate, aren't they? Well, in Physics 0625, doing exactly that is going to instantly destroy your mark. See, your calculator is mathematically correct, sure, but it is entirely scientifically ignorant. It has absolutely no clue what physical apparatus you actually use to get those numbers in the first place. And this is exactly where ordinary revision completely falls flat. Students spend hours and hours memorizing complex formulas, but they completely forget this hidden half-a-division rule for recording data. It all comes down to the number 0.5. That tiny little number secretly dictates your entire grade in the Practical Skills Workbook. It's not just about doing the math, guys. It's about understanding the actual physical limits of the universe you're trying to measure.
Framework Step 1. Apparatus Precision. Let's dive right into this framework, starting with the absolute limits of the tools you're using. Okay, the very first concept you have got to master is the precision of measurements. Look, every single measurement you take in a lab is really just an attempt to find a true value, but it's always subject to errors, right? Because our apparatus has limitations. The golden rule here, and literally what Cambridge examiners base their mark schemes on, is that precision is usually taken as half a small division of the scale of your measuring device. You simply cannot claim to know a value any more precisely than that. It's physically impossible.
Now, notice how clearly a device's smallest division maps straight to your recording precision. Say you're using a standard meter ruler. The smallest little line you can see on there is 1 millimeter. Therefore, the precision of literally any length you measure with that ruler is half of that division, so 0.5 millimeters. And it's the exact same logic for a thermometer. If the marks are at 1 degree intervals, your precision is 0.5 degrees. If your data table doesn't reflect this exact precision, the examiner knows instantly that you don't really understand your own equipment.
And here's something you really have to keep in mind. Precision becomes a much smaller proportion of your measurement the longer the length you're actually measuring. This is a massive, game-changing concept for evaluating how reliable your experiment is. If you measure a full 1 meter length, so 1,000 millimeters, with a precision of 0.5 millimeters, your error is only 1 part in 2,000. That is highly reliable. But if you use that exact same ruler to measure a tiny 1 centimeter object, suddenly your precision is 1 part in 20. The same ruler gives you a way larger percentage of error just because the object is smaller. Make sense?
Framework Step 2. Mastering Significant Figures. Now, listen closely. In just a moment, I'll show you the exact examiner clue that changes the final answer completely. But first, you absolutely need the framework that makes that clue obvious. And that framework is mastering significant figures. Significant figures are, simply put, the number of digits given for a measurement or a calculated value that show how accurate we genuinely think it is. This right here is where that calculator trap snaps shut. You must never, ever give more digits in a calculated answer than are actually justified by the apparatus you used.
So the crucial point is knowing exactly how to count them. Take the value 6.7. That's 2 significant figures. The value 0.235, that has 3 significant figures. The 2 is the most significant, and the 5 is the least. And hey, pay special attention to standard notation. If you've got 6.24 times 10 to the power of 2, only the digits before the power of 10 actually count. So that gives us 3 significant figures.
Okay, let's apply the rounding rules, which are absolutely essential when you need to trim down that wildly long calculator output we talked about earlier. You just look at the digit following your last significant figure. If that following digit is less than 5, you just round down. Boom. So 1.23578 rounded to 2 significant figures just becomes 1.2. But if the following digit is 5 or above, you round up. That exact same massive number, if we round it to 3 significant figures, becomes 1.24. So this brings us to the ultimate sequence for solving calculation questions without bleeding your hard-earned marks. Step 1. Do the math and calculate your values. Step 2. Pause, look back at the original data provided in the question, and check their significant figures. Step 3. When you're calculating a quantity using values with different numbers of significant figures, always, and I mean always, quote your final answer to the smallest number of significant figures used in that raw data.
The Interactive Examiner Challenge. Let's move on and actually see how this builds by challenging you with a real exam scenario. I want you to put on your examiner hat for a second.
Take a look at these two answers. Assuming the original measurements provided in the question, say the length, width, and height of a wooden block, only had 2 significant figures. Can you spot why the flawed answer on the left throws away those easy marks? The student wrote volume equals 45.234 cubic centimeters. They did the math perfectly, but they failed the science. The top-end answer on the right boldly chops it down to just 45 cubic centimeters.
And this brilliantly illustrates the core feedback from Cambridge examinations. You cannot magically create precision out of thin air just because your Casio generated some extra digits. If your ruler only gave you 2 significant figures of confidence, your final volume cannot miraculously possess 5 significant figures of confidence. The mathematics literally has to reflect the physical reality of the apparatus.
The diagnostic cliffhanger. So, you've mastered apparatus precision, you've mastered significant figures, you're rounding perfectly based on your raw data, but I have to warn you, there is still one hidden trap waiting for you on exam day.
Imagine this nightmare scenario. You got the numbers absolutely right. Your units are flawless. Your significant figures perfectly match the smallest number of sig figs in the raw data. You did everything we just talked about, and yet, the examiner draws a big red X across your page. How on earth can you still score 0 marks? Well, it happens all the time. It happens because you got the numbers right, but you failed the command word of the question. You evaluated when you should have described, or you explained when you were just supposed to state.
The numbers are really only half the battle. Knowing exactly what the examiner is asking you to do with them is the whole other half. If you don't know your command words, you are flying blind. Subscribe to our YouTube channel, Ace the Exams, at @ACEXams_IGCSE, to excel in your Cambridge examinations. And join me in the next explainer to reveal the precise command words that dictate your final grade. Will your next calculation score a perfect 10 or a 0 in disguise? You have to click the next explainer right now to find out. I'll see you there.